Hello, my name is Sriram Krishnamurthy, and I'm going to be talking about how the vDSO plays a role in Linux RISC-V architecture runtime. Let's first start by defining what a Linux kernel system call is. There's specialized routines in the Linux kernel where user space applications perform specific tasks such as writing to a file, reading from a file, getting attributes of various kernel addresses, or performing any privilege-required tasks in the kernel. Now, what is a virtual system call? Virtual system calls are applications that accelerate the execution of a kernel system call by mapping it to the user space, resulting in the system calls having set physical memory allocations. However, this design choice may result in vulnerabilities due to ease of access and ability to exploit the kernel call. Now let's define what a virtual dynamic shared object is, or the vDSO. Well, as I said in the name, it's a shared object providing various system calls or functions to the user space by the kernel mapping these calls in all address spaces of user space processes without requiring invoking of a full system call. It can be considered an optimization of the virtual system call because it maps system calls to the user space, which are various programs and libraries that the Linux OS uses to interact with the kernel. Therefore, instead of switching to kernel mode to access certain system calls, the user space will have the location of a small set of system calls readily available and can access them through the address map on the vDSO. However, this does not apply to all system calls in the Linux kernel, which we will clarify. There are various differences between vDSOs and virtual system syscall objects. The vDSO is dynamically initialized upon every iteration of the kernel being built, while the virtual system call is statically initialized in address and location. In addition, the vDSO stores the virtual memory locations of a few kernel-level system calls, mainly time-related system calls, so that the Linux kernel can map it to the user space to be quickly accessed. Virtual system calls are simply ways to statically map kernel space system calls onto set physical addresses in the user space. However, the difference between the two is the lack of security from virtual system calls, unlike the vDSO, which is mapped to every process in the user space and is dynamically initialized, thus preventing the possibility of accessing the vDSO from anywhere and ensuring that certain system calls can function on a set reference. Here's a diagram of how to initialize the vDSO. You have the base address of the vDSO attained through the AT_sysinfo header tag, which is fed into each Linux program within the kernel. These Linux programs are fed into the initial auxiliary vector, which contains the access point for every program that can be used in the user space. The vDSO base address is randomly generated during initialization and is loaded with the vDSO into each Linux process's address space as a shared object, separate from the kernel's dynamic linking system. The AT_sysinfo tag can also be used, as stated previously, to provide the entry point to each virtual system call and fed into the initial auxiliary vector as a backup if the AT_sysinfo header tag provision does not result in retrieving the entry point to each system call in the Linux kernel. Finally, the auxiliary vector's data is then read in by the ELF object loader, which takes the vDSO as a shared object and the rest of the Linux kernel data from the initial auxiliary vector and maps the Linux system calls to the user space. Now, this is a diagram of how the vDSO is initialized on both the kernel and user space ends. The kernel space is the operating space of the kernel, is responsible for maintaining the system's resources such as CPU, memory, and storage, and provides system calls allowing user space applications to interact with the kernel. This has unrestricted access to the resources of your Linux system. The user space, on the other hand, is where front-end user applications run, and they cannot directly interface with the kernel's resources, so they need a way to link to these resources. What other way but virtual system calls? So to initialize the whole setup, the vDSO image needs to be created first. This is then loaded onto the user space by the ELF object loader, and the libraries or system calls are stored on the object, the vDSO, are linked to the user space through a dynamic linker after finding the address of the vDSO. And these libraries on the vDSO normally consist of time-based functions, such as get time of day, clock get time, or even get CPU functions, which we will be demonstrating in the live demo later. To enable the vDSO, the kernel must be MMU enabled. So let's go over. What is the MMU? It stands for the Memory Management Unit, which is used to manage the virtual memory and translate it to physical memory for the user space. Translated addresses are stored in the TLBs, or transition look-aside buffers, which are then read by the table walk units in the MMU, into the caches to be stored in the translation tables in the physical address area. Without this, the vDSO stored addresses for the user space will not be able to be accessed properly. Now I'm going to do our live demo. We're going to run through a few implementations of system calls that are specific to the vDSO. These are mainly time-based system calls that were specified previously, like clock underscore get time, the get time of day, or the get CPU. I want to emphasize the effect on runtime that the vDSO has on each of these system calls when enabled and disabled. And then we're going to be performing, and then we'll just show one or two static system call implementations without the vDSO. So I'm going to be running through a few system calls implementing the vDSO and see how they perform with the vDSO enabled and disabled. So I just thought I would run through some tests, each containing different system calls. So the first one would be the first one that I'm going to run through is the get time of day system call. The second one I'm going to run through is the get CPU system call, and the third I'm going to run through is the clock underscore get time system call. So first, let's run through. Let's run through this one, the shell get time of day. So first, I'm going to run through the system call, calling it 100,000 times. The reason why I'm not calling it only once is because in order to see if there's any overhead, then we have to run it for a very long time. So let's do it. So first we are going to compile. Then we're going to do that, and then we also, so to be first off to toggle the system to toggle the vDSO, we have to go into the kconfig file specific to the architecture of the Linux kernel that you are using. At first, I thought it was just for the config file of the kernel, the regular config file of the kernel that was stored in our subdirect or GitHub Linux subdirectory, but it was actually the architecture specific kernel. So first we are going to, we're just going to be running through them without the without the vDSO enabled. So yeah. So as you can see here, the reason why there was actually an error, why there was an error is because we don't have MMU enabled. So in order to make that, so in order to fix that, we have to go to menu config. There we go. Yeah, so we can see that it ran all right. So now we're going to now we're going to try running the next system call. You can see here it's also good. And now for the third and last one. Okay, so that is also good too. Now we're going to try to shut off the now we're going to try to shut off the um shut off the vDSO or disable the vDSO to see what happens. So first we have, so I'm just toggling it. I'm just toggling the have underscore generic underscore vDSO config tag in here. So now let us go back. Okay, so here you can see without the vDSO, some get time of day, the get time of day and clock underscore get time commands are not able to be accessed because they are vDSO specific. So Therefore, their addresses are not able to be sent to the VDSO. Their addresses are not able to be sent to the initial auxiliary vector, and are not able to be unloaded by the ELF loader to for the kernel to actually map these system calls to the user space. So now, if we go in, but now, what will happen if we just disable certain parts of the certain features from the VDSO? Like select generic get time of day. Oh, and select generic get time of day. So now let's do this. So now we're going now let's run let's run it without the generic get time of day. Okay, still it has that error. And the reason why is because, yeah, the get time of day function is not imported. So now, what if we do generic vDSO time in nanoseconds? Let's see what happens with that. Kernel build took a very long time. Might likely because of the lack of vDSO time being available in nanoseconds, but let's see how it performs. Okay, so we're still able to perform well with that. The clock get time system call, but what about the others? Okay, so seem to have taken all right. So in this case, it actually seemed to stall because until I press the enter button, likely because of the lack of time being available, because of the VDSO time in nanoseconds not being available. Now let's see what happens when we run with the other two. Now, yeah, let's see what happens when we re-enable when we re-enable this and then disable another command. So I just disabled just the generic VDSO time rather than time in nanoseconds. So now let's see what happens with that. Okay, so in this case, it actually did not compile because of the time not being because the generic VDSO time was not available, even though the VDSO was available. So I guess getting some of the system calls from the VDSO, like for get CPU as shown here, and also for getting some of the values for time, were not enabled. So now we're going to test with one with a couple of static calls. And yeah, basically I'm just going to be running one program here to see what happens for the static calls. And the static calls, they include write and read. So I'm going to be seeing what happens there because normally write and read wouldn't depend on other system calls. So we're going to see what happens with that. Okay, so in this case, I guess it still requires the VDSO, given that it is MMU enabled, because it still requires the memory map addressing. So yeah, I guess in conclusion, the VDSO is required for both static and dynamic calls, and otherwise, some of these VDSO specific system calls will not have access to will not be able to be accessed since since the VDSO address and their addresses are not accessible by the are not accessible by the ELF object loader for the VDSO. So that is it for my demo. Thank you very much for watching. So, having seen the vDSO live demo, here's how we learned it can be ruined. Since some applications require the vDSO, they will end up depending on each other as shown in the demo. And the vDSO requires the MMU, or the memory management unit, so if we shut it off, then this prevents the mapping from virtual to physical addresses, which makes it much more difficult for the vDSO to actually get the location of their designated system calls to be sent to the user space, which effectively kind of just crashes the kernel, as we saw. In conclusion, the vDSO is an important tool for speeding up access to kernel level system calls. It provides user space access to a set group of system calls and requires virtual to physical address mapping. And we also learned that static system calls require the vDSO as much as dynamic system calls. So, and also, even the calls that we consider to be static and have set physical addresses and do not supposedly don't depend on other system calls do end up depending on other files. So in a sense, most Linux system calls are not static. Thank you very much for listening to my presentation.